Welcome to the last challenge in this particular course, and in this challenge we'll be predicting the medical expenditure of a patient. So we are given a data, and using that data, the inferences and the analysis, we'll be predicting the medical expenditure of a patient. Okay, so first of all we'll be importing our libraries. These all are libraries we have. Okay, and along with it I'm loading the data. So the data is named as medical cost data. It's a CSV file. Okay, let's check our data. So you can see that's the data we have. So we are given age, sex, BMI ratio, that is body mass index, number of children a patient has, whether a person is a smoker or not, the region it belongs to, and the charges, right? Let's check the data info as well. So that's the data. Data is looking completely fine. Let's check the data description. Okay, so here's the data description, and let's check the null values as well. Well, it's being looking perfectly fine, but being on the safer side, let's check it once. So is null dot sum. Okay, so you can see that we have no null values in our data, but you can see that our data has three categorical values: the sex of the patient, whether the person is a smoker, and the region. So what we'll do is we'll convert this categorical data to a numeric form, and for doing so what we are using is we are using label encoding. Okay, also let me show you the distribution of these columns that we are having. So unique, okay, so these are the two labels that we have in sex column. Then we have our smoker, so it will be yes or no. Okay, so you can see that it's either yes or it's no. Then we have the region, and let's check the unique values this region column have. So we have four different unique labels in the region parameter, and now it's time to encode our labels, right? So what we'll do is we'll convert this categorical data to a numeric form, and for that we'll be using a label encoder. For importing that, we'll simply use pre-processing module of scikit-learn. So scikit-learn dot pre-processing, and then we'll import the data. So label encoder, and we have to prepare the label encoders for all the parameters we have. So let's initialize this label encoder, right? And then we'll fit our data to it. So le dot fit. So placing the data, so data dot 6 dot drop duplicates. We don't want any duplicates in that. Okay, so here we go. Similarly for the smoking data we have. Okay, wait a second. So data dot sex equals to le dot transform and the data we have, so data dot sex. Okay, let's copy this one. We'll do the same process for other three parameters. So label encoder we have initialized. We have to fit the data smoker over here, right? And then changing the data smoker and passing the data smoker, right? Similarly for the region, so region, okay, so sorry, it's from. Okay, so here we go. We have converted our data to a numeric form. Let's check our data. So data dot head. Okay, so now you can see that's our data. Everything is in numeric form. Let's check the previous data we have. So you can see that this was the previous data. Now you can see that female, male, and yes, no. And similarly over here, so what I giving 0 1, so it was female, male, so it is 0 for female, 1 for male, and here it has converted in the form like 1 for yes and 0 for no. right? So this is how the label encoding technique works, and our data is now ready to perform the further analysis. In the next coming lecture, we'll be understanding how we can analyze our data so as to select the best models to predict this particular value. So it will be needing a regression model to do so, because the data labels we have are not unique or discrete, so we have to use a regression model. Till now we have seen our data and we have converted our categorical data to a numeric form. And now it's time to understand and analyze our data to see which parameters are very important to predict the charges of a patient. Okay, so first of all, what we'll do is we'll find the correlation of our parameters with the output parameter using a heat map. So for that, what we have to do is we'll simply use data, and then we have to find correlation of parameter. So we have to find correlation of parameter charges with respect to rest of the parameters, right? So we'll mention charges and we'll say sort values accordingly, right? So you can see that that's the particular correlation value with respect to the charges. So you can see that a smoker is having the higher correlation with the parameter charges. That means if a person smokes, then the chances of higher charges are more. So it is directly proportional with respect to charges. Also, the age is directly proportional to the charges. The more the age, the more will be the medical expenditure. So it's quite obvious, and our data is showing the same. That means if you are aged and if you smoke, then you have higher medical charges, right? So the probability of the charges will increase, right? And similarly, the religion, as you can see, is having a negative correlation. So, well, it doesn't have much of the correlation with respect to the charges parameter, right? So this is how we analyze our values. We can plot this also using the Seaborn library. So for that, what we have to do is we have to mention the figure size and the axis. So we'll say plt dot subplot, and then we have to mention the fig size equals to, so the figure size will be, let's say 10,8, and then we have to mention the correlation. So it's present in data dot correlation, and then we have to mention the heat map that we want, passing in the parameter. So what parameter we require? We require correlation, then axis equals to axis that we have already mentioned over here, and then the annotations be true, that is the label of the heat map. Okay, so you can see that's our heat map, right? So this is the color convention that we are given. You can see that each parameter is highly correlated to the same parameter, right? Those charges will be 100% correlated to charges. That is quite obvious. But now we have to see the correlation of other parameters with respect to charges. So the smoker parameter is having the highest correlation with respect to charges, and then the age, right? So let's analyze the smoker parameter individually. Okay, so for that, what I'll say, I'll plot a factor plot. So SNS dot factor plot, then we have to mention the data. So x equals to the smoker parameter, right? And what kind we want the count of it. Okay, sorry, so we have to mention it, count, and then which parameter to take in consideration. So let's say 6. So we'll compare the male and female counts individually. So data equals to data, right? So now you can see that's our data. Now let me show you one thing. So male and yes no, right? So we have a convention, that is females are assigned 0 value and males are assigned 1 value. Let me show you again. So you can see female, male and yes, no, right? And then when we converted it to numeric form, the females were assigned 0 label and males were assigned the 1 label, and yes was assigned 1 label and no was assigned 0 label, right? So when we are discussing it over here, so you can see that we have 0 and 1. So 0 means female, right? So this is for females. And wait a second. Okay, so now what we can say that 0 means that a person doesn't smoke. So these are non-smokers, right? And these are smokers. So the count of non-smoker is higher in our data and the count of smokers is very less in our data. And you can see that the person who smokes, the males are having higher number with respect to the females, right? So we can say that the cost of treatment in men will be more than women given the impact of smoking. So if we are considering this smoking parameter, if a person smoke and if a person is a man, then that person is having a higher chance to a woman who is smoking. And if a person is non-smoker, then in those cases the females are having higher medical cost with respect to men. So this is a smoke analysis, how the smokers costs are effective. And now we'll be comparing the BMI index. Okay, so for that what we'll use is we'll simply we'll simply plot a disk plot so we can see the distribution of our BMI. So we'll say X equals to SNS dot disk plot, and we have to mention the data. So data and then the parameter we are talking about. So we are talking about BMI. So wait a second. Okay, it's giving an error. So actually it's disk plot. Okay, so it's disk plot, distribution plot, right? So you can see the distribution over here and we can clearly see that the average BMI of our population, that is the total entries in our data, based on that the average BMI value is 30, right? And now we'll be checking the children count. So we'll say SNS dot factor plot and we'll mention the data X equals to children kind equals to count and then data equals to data and then the size equals to 6. Okay, there is an error. Actually, data is a variable, we don't have to mention it in string form. So yeah, that's our data. So you can see that most of the patients don't have children, right? And now in the next coming lecture we'll be splitting our data and we'll be preparing our machine learning models. So the data we have to do is this final data. So this was all for this lecture. What we'll do is we'll split our data, and for that we have to prepare our input and output data. So the input data will be, as you can see that we have this particular data. So what we want is for the inputs we will drop these two particular columns, region and charges. As charges we have to predict, that's the output, and the region is not doing any significant contribution in predicting the charges. So what we'll do is we'll say data dot drop and then we have to mention the columns. So we'll say data dot columns, then mentioning the data 6, 5, and then we have to mention the x's. Okay, and then we have to prepare our output. So our output will be data, and which column is we require, that is the charges, right? So that's our input and output. So that's our input values. Okay, and now we'll split our data using the train test split model in the ratio 70-30. Okay, and now we'll feature scale our data. Why? Because the data we have is having different distributions, so we'll scale our data. So we'll do it using the min-max scaler. So from sklearn dot pre-processing wait, pre-processing, import min max scalar, right? And then initializing our min max scalar. So that's our min max scalar. We have initialized the min max scalar. We are fitting our data and we are transforming the train and test data. Okay, so that's it. So you can check the first entries of our data now. So 0 is to 2. So you can see that that's our data. Everything is being arranged in the range 0 to 1. And these are our machine learning models. We are using linear regression, decision tree, support vector regressor, and random forest regressor. So our models are initialized now, and then we'll be fitting our models and we'll train it. So the models are trained now, and then we'll be predicting our results. The prediction results are in these variables, and now we'll be comparing the root mean square values of our results, right? So that's the result we have. You can see that linear regression, then decision tree, then support vector, and then random forest. So random forest is giving the best results out of all. It's predicting the cost of our expenditure with this particular RMSE error. The error is high because we have a very limited data. So this is how we work on our data, where we have to use a regressor model. So this was all for this lecture. Best of luck and keep following.